In the last few videos, we have been looking at rotors and how they can be used to rotate vectors. To rotate a vector by an angle theta, we need to use the rotor created by multiplying two unit vectors with an angle of theta between them. Is there any shortcut to finding this rotor? That is what we will answer in this video. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. The fundamental question of this video is this: given an angle theta, how can we find a rotor that represents rotating by theta? While there are direct answers to this question, we will take a very different route. While it may take a while, the answer we will end up with will be incredibly useful. Our starting point will be the exponential function. There are already many videos about this function out there, but to emphasize the aspects that will be important for us, I will give a quick exponential explanation of my own. Imagine a bank that gives you 100% interest, compounded annually. If you start with $1, you will have $2 the next year, $4 the year after that, and so on. However, the interest could get compounded more often. If it's compounded biannually, you'll end up with $2.25 after the first year. If it's compounded every month, you'll end up with about $2.61 after a year. It may seem like you'll get more and more money if they compound more and more frequently, but there's a limit. If it's compounded continuously, you'll end up with about $2.72 after a year. This is precisely equal to the mathematical constant e. In the end, the amount of money you will have after x years is e to the x. So e to the x is a function that represents continuous growth. In this example, the growth rate is 1. We can multiply x by some parameter r to change this rate. The growth rate will then be precisely equal to this value r. As r increases, the function grows faster, and as r decreases, the function grows slower. And the growth can even be negative with a negative rate. The important point is this: the exponential function represents continuous multiplication, with the precise behavior depending on the parameter r. Now, I want to pose what may sound like a crazy question. What happens if we put something that is not a real number in for the rate? For example, what about the bivector e12? Writing e to the e12 looks a little silly when the two e's represent two very different things, so let's replace e12 with its alternative name, I. So what would this exponential even be? Let's draw the result in the complex plane. First of all, when x is 0, e to the I0 equals 1. But what does it do for other values? Think about the original exponential function. It starts growing in the positive direction as x increases. But here, our rate of growth is not a positive value. Instead, our rate of growth is I, which represents a rotation by 90 degrees. So instead of growing towards the right, we end up growing sideways. But as we start moving up, sideways starts turning more and more to the left. In the end, we are always moving perpendicular to the vector going from the origin to our current position. Geometrically, if you move in a path that is always perpendicular to your current position, you end up traveling in a perfect circle, which is the unit circle here because we started at 1. Thus, e to the ix ends up traveling around the unit circle in the complex plane. Because 2D rotors are normalized complex numbers, this means that e to the ix is a rotor. But how fast does this travel around the unit circle as x increases? Does the path move quickly? Slowly? Does the speed change depending on how far along we are? Once again, think back to the basic exponential function. Its starting rate of growth is 1. Of course, once you get bigger than 1, the rate of growth changes, but at the start, it's 1. For e to the ix, while the starting rate of growth doesn't point in the positive direction, it still has a magnitude of 1. So at the start, the speed at which we are going around the circle is 1. But unlike in the normal exponential case, we never get further away from the origin. This means that the speed at which we move around the circle never changes. So e to the ix will go around the unit circle at a constant speed of 1. Let's look at a few examples of what e to the ix equals for particular values of x. E to the I1, or just e to the I, is 1 unit around the outside of the unit circle. E to the 2i is here, and e to the 3i is here. At some point, e to the ix equals 1 again after going one full turn around the unit circle. Well, we know that the circumference of the unit circle is tau, which is equal to 2 pi in case you're not familiar with tau, so e to the I tau equals 1. We can also find a few other notable values of the complex exponential function. Halfway around the circle is e to the I tau over 2, 1/4 of the way around the circle is e to the I tau over 4, 3/4 of the way around the circle is e to the 3 I tau over 4, and so on. So how do we find a rotor given a particular angle? Well, we just need to find the distance along the outside of the circle that corresponds with that angle. Then we can take that distance and calculate e to the I times that distance. In fact, if we measure our angles in radians, that distance and that angle are equal. Because of this, we often just say we are exponentiating I times the angle. It's important to remember that when making rotors like this, the angle has to be in radians. But there may be one thing nagging at you. How in the world do we actually calculate a complex exponential like this? Well, we know that e to the I theta is the point on the unit circle at an angle of theta in the complex plane. From trigonometry, the x-coordinate of this point is the cosine of theta, and the y-coordinate is the sine of theta. So in the complex plane, this point is just the cosine of theta plus I times the sine of theta. Thus, we get the formula e to the I theta equals cosine theta plus I sine theta. This formula is called Euler's formula. Again, it is only valid when using radians. Using this formula, we can calculate any complex exponential we wish, and as a result, we can calculate rotations by any angle. Let's look at an example. Say we wanted to rotate the vector 3e1 plus 2e2 by 27 degrees. We first need to convert the angle to radians. Then, we just calculate the vector times e to the I times the angle. Let's do an exercise. Just like 2 videos ago, I am going to give you 3 vectors and 3 angles to rotate by, for a total of 9 rotations. Please pause the video and calculate these rotations. Taking a hint from when we did a similar exercise a couple of videos ago, let's calculate the rotor for each angle first. We just need to convert each angle to radians, multiply it by I, and then exponentiate the result. We get these rotors. Now, to calculate the rotations, we just need to multiply each vector by each rotor. Let's think back to the product of unit vectors. We know that the product of 2 unit vectors is the rotor representing the angle between them. We now know that this rotor is equal to e to the I theta, meaning that uv is equal to e to the I theta. Now you may be wondering, what about non-unit vectors? Well, we can do the same scalar algebraic trick that we have done before. For the product of 2 arbitrary vectors, we can multiply and divide by their magnitudes and then pull the magnitudes out, leaving normalized vectors. Then, the product of the 2 unit vectors is e to the I theta, producing this equation for the product of 2 arbitrary vectors in 2D. Given that the product of 2 vectors is the sum of a scalar and a bivector, we can use this formula to produce equations for the scalar and bivector parts of a vector product. The scalar part is the cosine of theta times the magnitude of each vector, while the bivector part is I times the sine of theta times the magnitude of each vector. We can also write these equations more succinctly by using the grade projection operator. Now, you may be wondering, if exponentiating bivectors produce something this useful, can we exponentiate other multivectors? And will doing this produce anything useful? First of all, yes, it is possible to exponentiate any multivector. In advanced contexts, we can define the exponential function using an infinite series, and this series happens to converge for all multivectors. However, it turns out that finding the exponential of arbitrary multivectors isn't that useful. So you don't really need to understand how it works in general. We will only ever need to exponentiate bivectors in this series. Now that we have figured out how to do two-dimensional rotations, we will next look at some of the applications of this way of doing rotations. For example, what do we get by sandwiching one vector inside another? That is what we will answer in the next video.